In 1948, a young physicist named Richard Feynman wrote down an equation so beautiful it would change the way we understand reality. It was a single mathematical principle, hidden inside a strange new formulation of quantum mechanics, and it carried a quiet, absolute warning. There are some things the universe simply does not allow. Nearly 3 decades later, in 1976, the most celebrated theoretical physicist alive, Stephen Hawking, would stand up and announce a discovery that violated that exact principle. He didn't realise it at the time. Almost no one did. But Feynman's mathematics had already ruled out what Hawking was about to claim, more than 20 years before Hawking ever wrote his paper. What followed was a 40-year intellectual war that would split physics in half, drag in Nobel laureates, force the greatest mind of a generation to publicly admit defeat, and reveal something so strange about the universe we still struggle to accept it. This is the story of how Feynman's deepest principle predicted Hawking's greatest mistake. And by the end of this video, you'll understand why being wrong in physics is sometimes the most productive thing a genius can ever do. To see why this story matters, you have to understand what Feynman was really doing in 1948. He had just published his path integral formulation of quantum mechanics. On the surface, it looked like just another way of doing the same calculations Niels Bohr and Erwin Schrödinger had done decades earlier. But underneath, Feynman had quietly re-engineered the foundations of physics itself. In Feynman's picture, a particle moving from one point to another doesn't take a single path. It takes every possible path through space and time simultaneously, and reality emerges from how those paths interfere with each other. From this strange and beautiful idea, one rule above all others crystallized. The total probability of all possible outcomes must always add up to 1. Always. No exceptions. Physicists call this principle unitarity, and it is the deepest law underlying all of quantum mechanics. Feynman didn't just prove unitarity, he made it visible. He turned it into the very language quantum physics was written in. And unitarity has a consequence so profound that even most physics students miss it entirely. Information cannot be destroyed. Ever. You can scramble it, hide it, encrypt it beyond all recognition, but the universe always remembers. Burn a book, and in principle, every word is still recoverable from the smoke and ash. Drop an encyclopedia into a bonfire, and the heat, light, and gas leaving that fire still carry every letter, every page, every comma. Feynman's mathematics was telling us something almost mystical. Reality has perfect memory. This is what made Feynman's principle so absolute. It wasn't a guess. It wasn't a philosophical preference. It was baked into the very structure of every quantum calculation he ever performed. And it carried a silent warning to anyone who would come later. If you ever discover a process in nature that seems to destroy information, you have not discovered new physics. You have made a mistake somewhere. Feynman died in 1988, never knowing that his warning had already been ignored. 12 years before Feynman's death, in 1976, Stephen Hawking did something remarkable. He combined Einstein's general relativity with the quantum field theory of empty space and applied it to the most extreme objects in the universe, black holes. The result was extraordinary. Hawking proved that black holes are not eternal. The vacuum near their event horizon is constantly producing virtual particle pairs, and one of these particles can escape while the other falls in. Over astronomical timescales, the black hole slowly leaks energy out into the cosmos, shrinks, and eventually evaporates completely in a final flash of light. This radiation is now called Hawking radiation, and it remains one of the most celebrated theoretical predictions in modern physics. But buried inside this triumph was a horror. Hawking's calculations showed that the radiation pouring out of a black hole was perfectly thermal. It carried no signature, no memory, no fingerprint of whatever had fallen in. Whether you tossed in a piano, a planet, or the entire works of Shakespeare, the radiation that came out was identical. And when the black hole finally died, every detail of what it had ever swallowed was, according to Hawking, gone forever, erased from reality. This was the claim that violated Feynman's principle. Hawking had just announced, with full mathematical confidence, that black holes destroy information. To understand why this was such a catastrophe, picture two identical black holes. One has eaten the entire Library of Congress. The other has eaten an equivalent mass of empty hydrogen gas. According to Hawking's 1976 calculation, after both have evaporated, the universe contains exactly the same final state. There is no measurement, no experiment, no calculation, no godlike observer who could ever tell you which black hole had eaten the books. The past has been deleted. And this is exactly what Feynman's path integral mathematics said could not happen. Unitarity demanded that those two scenarios end in two distinguishable final states, because they began in two different initial states. Hawking's claim and Feynman's principle could not both be true. One of them had to give. The deepest law of quantum mechanics, or the most beautiful prediction of black hole physics. The physics community froze, and then it went to war. The first to declare battle was Leonard Susskind. He read Hawking's paper and refused to accept it. To Susskind, abandoning information conservation was not just a technical concession, it was an act of surrender. Joining him was the Dutch Nobel laureate Gerard 't Hooft, a man with an almost spiritual devotion to mathematical consistency. Together, they formed the Resistance, with Feynman's unitarity as their banner. Hawking, on the other side, was unmoved. He doubled down. He stood in front of conferences and insisted, repeatedly, that quantum mechanics itself would have to be modified to accommodate black holes. In 1997, he made the disagreement official. Together with Kip Thorne, Hawking placed a public bet against the physicist John Preskill. The wager was an encyclopedia of the winner's choosing. The stakes were the soul of physics itself. The argument turned conferences into shouting matches. Friendships were tested. Susskind himself would later write a book about it called The Black Hole War, and he was very careful to note that the war was strictly intellectual. But it was no less ferocious for that. Either Feynman's deepest principle survived, or Hawking's calculation did. There was no middle ground. The breakthrough came from the most unexpected direction: string theory. Susskind and 't Hooft proposed something so strange it sounded like a fever dream. They called it the holographic principle. The idea was that all the information inside any region of space, including a black hole, can be encoded entirely on its two-dimensional boundary, like a cosmic hologram. Nothing falling in is ever truly lost. Every detail is smeared across the event horizon, waiting to be read out by the radiation leaving. Then, in 1997, the same year as Hawking's bet, an Argentine physicist named Juan Maldacena gave the holographic principle a precise mathematical foundation. He called it the ADS-CFT correspondence, and it was the bombshell that shattered the war. Maldacena showed, through rigorous calculation, that the physics inside a region of curved spacetime could be perfectly described by ordinary, fully unitary quantum mechanics on its boundary. There was no information loss anywhere. Feynman's deepest principle had not just survived, it had been confirmed at the most extreme conditions in the universe. By 2004, the writing was on the wall. At a conference in Dublin, Stephen Hawking himself stood up in front of the entire world's physics community and conceded the bet. He delivered a baseball encyclopedia to John Preskill, joking that information could be retrieved from it at will. The most famous theoretical physicist of his generation publicly admitted he had been wrong. Hawking's greatest mistake had finally been corrected, nearly 3 decades after he made it. And the principle that had ruled it impossible from the very beginning was the same one Feynman had quietly written down in 1948. But conceding a bet doesn't fully solve a paradox. It took another 15 years before physicists finally worked out the mechanism in detail. Around 2019 and 2020, a new generation of theorists computed something called the page curve and showed precisely how information leaks out of an evaporating black hole through subtle quantum effects involving wormhole-like geometric structures. The mathematics was breathtaking. It confirmed, once and for all, that the radiation leaving a black hole is not thermal in the way Hawking originally calculated. It is deeply entangled, deeply structured, and carries every bit of information the black hole ever swallowed. Reality really does have perfect memory. Just as Feynman's path integral had insisted from the start. So what does this story actually teach us? It teaches us that Feynman's deepest principle wasn't just a piece of mathematical machinery. It was a warning written into the foundations of nature, decades before anyone needed to listen. It teaches us that even the greatest minds in history can be wrong, and that being wrong in exactly the right way can be more valuable than being right. Hawking's 1976 mistake forced us to discover the holographic universe. It forced us to find ADS-CFT. It forced us to understand that gravity, quantum mechanics, and information are bound together in ways no one had ever imagined. The man who started the war lost it. But because he started it, we now understand the cosmos a little bit better than we did before. And quietly, in the background, the ghost of Richard Feynman still smiles. His deepest principle predicted Hawking's greatest mistake more than 20 years before he made it. And it's still standing today. If you enjoyed this dive into one of the greatest intellectual battles in modern physics, hit that subscribe button, smash the like, and let me know in the comments which side you would have backed in 1976. Until next time, keep questioning everything.